can do to help out. What do we got? Any more comments here? Yeah, it's just kind of the way it is. I hope you guys are doing all right. Today, I hope you guys got the message there about a scientific calculator. I guess you don't have to go and buy one. There should be one on your laptop or somewhere. This week here, we'll start using the scientific notation and all the funky things there for your calculator. And I hear you. Remote learning is brutal. I miss being in the classroom, and I miss seeing you guys in the hallway. Like, hey, John, where's your assignment? I need that. I miss that kind of. That's just teachers, and but the people who have had issues that I know of, you guys have been very forthright about emails. I love it. And let me know if anything's happening. I just checked there, and the labs, for the most part, are all in. I hope that there wasn't too much confusion with that quiz. It was the first time I used it, and sorry, you guys were my guinea pigs. Haha. But I think it all got done, and I heard some hooting and hollering, and I take it all under advisement. I really do. I don't take things personally. I know where I'm at in the universe. I know I'm okay with what I'm doing, so I can take constructive criticism, and I just use it just to make it better. So don't feel afraid that I'm some tyrant and, oh, what, you didn't like that? Oh, well, then, No, I'm not perfect. And I'm just we're all trying to do the best we can, and I'm trying to hit all these different types of learning styles. Social learning, individual learning, tactile learning, auditory, visual, all these kinds of things. Social learning, that's the big thing that we're kind of missing here, is you guys getting together and cramming there one night there before an exam. 6 people, you got 2 coffee machines, you order some pizza, that whole thing, and you cram it out and you get A's. That's how it's done. But it is what it is. May I offer a suggestion? Create a Facebook group. Create a WhatsApp group. Label it as Chem1009. And, so it's it's not, you don't open up a group there to socialize. It's 10 o'clock at night on a Wednesday and you can't get question 24. You post, hey, is anyone else having issues there with question number 24? I've done it twice. I can't get the answer. And somebody emails you back. Yeah, Ian already updated the question there. Somebody found out about it. It's on the announcement. It's been updated. The question should be this, or something like that. And hi, Hunter. Nice to have you. And create a page there just for this class. Create another page there for your Phys. And what do we got here? So the quiz is due. I gave you an extra week on it. Doesn't really matter. Okay. Your assignment will go out there this afternoon. Actually, I can probably open it up right now. Nope. What do we got here now? I'm coming. So here we go. So it's under assignments. You guys can see this. And there it is. And I'll just make it available. So this is your assignment here. What I'm going to do is I've heard and I've listened and I'm going to accommodate the... I just want to make sure, am I sharing my screen or am I not sharing my screen? Sorry, I guess I'm not even sharing my screen. So you guys are just going looking blind. Yeah, okay, fine. Have a look here. I'm over here. I went into assignments and you guys were telling me there that some of you guys don't have printers. So may we please have a Word copy. So what I've done is I've created a Word copy and the PDF. So you can work on this however you choose. Just a when you're working out heavy-duty calculations, you will need a pen and paper. Generally, that's how these ones go, like mathematics, right? So if you don't have a printer, have pen and paper. Do all your calculations, these on a scrap piece of paper, and then put the right answer in. So I'll have a look here. This is what your quiz or your assignment looks like. And I think it's 40 questions. And they're all multiple choice. And they're broken up into chapter 13 and 14. And what do we got there? 15. So that's it right there. Totally doable. You got 2 weeks. Talk to each other. And you see, this is how I would normally do it. And I would take paper copies there in class. But since there is no class, this is just for your own reference right here. So you guys can keep track of the answers. Or you could just circle them like a normal one. What I'm going to do there, hopefully there in the weekend, is I'll send out that emailed bubble sheet. The same thing, so you can fill in the bubbles and away you go. That's what'll happen. So that there is released right now, so y'all can actually get working on it. It covers weeks 1, 2, and 3. Next week, though, that's where things are going to get, and I'm going to introduce a little bit of next week there this week, and next week there is where we get some good calculations. So next week's is important, but this one here is important as well. So let me know how things are going. Other than that, I think we are doing really well. If we can take another minute, I can't really see my screen anymore because I'm sharing. So if anyone has anything to add to where we are now in week 3, let me know. We got a minute or two to chat, and if there's any serious emails, again, just email me. Okay? So if you're shooting comments, I can't see them. Just as you guys know, if you guys want to add something or ask a question, please interject at any time. Just take your microphone and turn it on and yabber away. Okay? If you guys got nothing, I got nothing. Let's go. First and foremost, I need to make sure that you guys are good to go on this. Scientific notation. So here we have 0.00753. Now it could be moles, could be grams, could be whatever. Number of molecules, doesn't matter. Okay? And the ability there to flip this into scientific notation. So we like to have the decimal right in here. Okay? And so if your decimal is, first of all, you have to think. Very first thing, is this greater than 1 or less than 1? Because if it's greater don't do that. If it's greater than 1, your exponent will be positive. If it's less than 1, your exponent will be negative. So here this is obviously less than 1. So I move my decimal 1, 2, 3 because that's where we like it. Why does a decimal go there? Because that's where we like it. End of story. So I move it 3 decimal places over to here. It's less than 1. So it's going to be 7.53 times 10 to the negative 3. Here I got 24,700. Okay, this is obviously greater than 1, so my exponent will be positive. Where is our decimal here? That ain't a decimal. That's a comma. So 24,000, my decimal is right here. We like our decimal right here. So it's 1, 2, 3, 4 spaces, 2.47. 2.47 times 10 to the 4. Now, I wanted to show you guys how do you enter 7.53 into your calculator. Okay? You type in 7.53 times, EXP to the negative 3. See right here. EXP button. Maybe yours will be times 10 to the something button. But that's how you do it. So let's say I wanted to copy. Okay. Now, is that still going to be? Yes, it is. So times, let's say I wanted to multiply. Just I get rid of this. I just wanted to multiply 7.53 times 10 to the negative 3 times 2.47 times 10 to the 4. How do I input this into my calculator? Well, 7.53 times 10 to the negative 3, that's how you would input it into the calculator. Do not use the... Do I have it here? No, I don't. Of course. Sometimes you'll see on your calculator like an x to the exponent y. Never use that one. For these guys anyway, okay? You only want to use the EXP button for these guys. You don't need brackets. If you're using, you just don't want to use any brackets. And this is the easiest way that I've found. So to input this into the calculator, okay, I would go 7.53 exponent negative 3. That correlates to this number. Times 2.47 EXP 4 equals. And trust me, when we get into Unit 2 there in physics, you're going to have like the mass of the Earth in kilograms divided by the gravitational pull of this. You're going to be dealing with wacko numbers. And the only way to get rid of them is just do this. Easy peasy. So I'm just going to test this out here. 7.53 exponent negative 3 times 2.47 exponent 4. So, and I got an answer of 185.991. Okay? So I'm just going to put this guy out. All right, so that's how, there's a little bit of a way of how we do this. So hopefully there you guys can replicate that. If there's any issues, let me know there this week, okay? Because when you guys are doing the assignment, you guys are going to have to do the same thing, all right? If you guys got nothing, I got nothing. Let's go. Welcome to acids, bases, and salts. Now, my question to you is, which is more dangerous, an acid or a base? Neither. Acids and bases can be deadly. But then, some acids can be very delicious. Tomatoes, vinegar. You know that tang there that comes from acids? You know that you squirt the lime juice on this if any of you are foodies, and it gives that brightness, that fresh, that little tang back here. That's an acid. And basically what I want you guys to know about acids is they are hydrogen producers. Hydrogen producers. Okay? And we'll get into bases. But acids there, they generally sour. They turn litmus paper red. Okay. They react with a number of things there. They react with metals to produce hydrogen gas. They react with bases to produce a salt and water. We'll come back to that one. And reacts with carbonates to produce carbon dioxide. I got one of those as well. So this is what we're looking for here. I'll get more into the definition there between a deadly strong acid and a yummy weak acid. And inversely here, we're talking about bases. What I want you guys to know from a base is that bases are hydroxide ion producers. Going back here, These guys here are hydrogen ion producers. Now you think about it. What is a hydrogen atom? What's its nucleus? What's its atomic number? If you go to the periodic table, it's 1, 1. So that means there that its atomic mass is 1, its atomic number is 1, so there are no neutrons. The nucleus of a hydrogen is a single proton. That's it. Just a proton with 1 electron going around it. That's all it is. So when you see a hydrogen ion, here's a good one. What is an ion? It's an atom with a charge. Okay? That's all it is. All the atoms you see on the periodic table, they are atoms. They're not ions. Once those atoms go into a chemical reaction and lose electrons or gain electrons, whatever they do, but if an atom gains or loses electrons now, it now has a charge. Okay? It has a positive or negative charge, right? Ions, cations, anions, right? So basically, an acid is a compound that produces protons. That's all it is. Because this is a hydrogen atom without the electron. Well, bases, they are hydroxide ion producers. And if you have a look here, what do you think? H plus OH produces H2O. Bases there, they tend to be slippery. Soap, right? Slippery. Bitter, I don't know of anyone here who would try. I guess you could eat soap. Don't. I didn't say that. Yeah, don't eat soap. But I guess it would be bitter. I don't know what soap tastes like. I don't know where they got this information, but it's bitter. Caustic. Soap has when you get into stronger acids and stronger bases, which we'll get into, they both can eat away. Like strong sulfuric acid, like a strong concentration of it, will eat through a table. Well, a strong base, if it's strong enough, will eat through the table as well. So they both have like bases tend to be, they use this word called caustic. It burns, like your oven cleaner, just burns everything. That's why it cleans nice and clean in the oven. Slippery, and they neutralize acids. Okay, but we'll get into all this there more. Which type of solution would have a sour taste and turn blue litmus paper red? See, perfect question. Love it. And the answer's already there. Let's keep going. Now, there are a number of different acid-base theories out there. And the one there that, this one here, it's called the Bronsted-Lowry acid and base. And a couple of these theories, they kind of work. I'll tell you which one there that you'll really need to know. But here, an acid is a proton donor, which is what we just said. And a base is a proton acceptor. Interesting. Keep this in mind. Bases are OH. All right? But have a look at this one here. Here I put some hydrochloric acid into a jug of water. That's all I did. And, well, in this case here, I bubbled it. It's a gas. And into some liquid water. And you see what happened here. We get this strange beast, apparently called a hydronium ion. And here we have a chloride ion. And you think, what happened here? And we can break it down using these structural formulas here. So here's my acid, and definition of an acid is a proton producer. So, and you see, one of these, I'll zoom in. Now, chlorine, 1, 2, 3, 4, 5, 6, 7, because it's in group 7, right? Hydrogen only has 1 electron. So you see that electron right there? That was given to the entity from hydrogen. But chlorine is such a massive atom. It has a molar mass of 35.5. Meanwhile, hydrogen has a molar mass of 1. So you've got this huge chlorine atom and little hydrogen. Who's going to be the big boss? Chlorine. So chlorine's going to scoop up hydrogen's electron. All right? So poor hydrogen. It's kind of just floating out here. But you see, have a look at your water, and this is one of the most weirdest molecules out there, but thank goodness it is. Water, this bent molecule, and you've got this oxygen here, who's the big boss against these two little hydrogens right here, and it's bent, but you have these two groups of electrons out here. So this side of a water molecule is negative, because you got 4 electrons sitting right there all by themselves, hanging out. So what happens is chlorine basically steals this electron, so this hydrogen here gets kicked out. All right, and where does it go? Choom, sits right there. So now, you see, you have this polyatomic ion. Polyatomic just means more than one atom. And you've got H3O+. This is what we're talking about as far as, if you see this, sometimes you'll see it written as H+, or sometimes you'll see it written as H3O+, sometimes you'll see it called hydronium ion. Whatever it is, it just means that this solution is acidic. And what does acidic mean? It's got a lot of hydrogens. Okay? It's those hydrogens there that give you the tang from the lemon. You know what I mean? That kind of a thing. So, going back in here. But I wanted to show you guys something. Can I do this here? Is it going to let me? Can I do it? Maybe I can move that up. No, I can't. I'm just going to move that over there. Okay. So, let's break this down. Very important. Not too bad to get, just follow me right here. So here I have an acid. It donated a proton to the water. The water accepted a proton. So in this case here, this water is a base, according to the Bronsted-Lowry acid and base theory. So here, this is an acid, easy peasy. But water is neutral, but it just means that anything that is accepting a hydrogen from an acid will be a base. So that means that here, water is a base. Acid, base. And what does it produce? The hydronium ion and a chloride ion. Now, and I'm going to start introducing this stuff now. They're this week for next week. The whole idea, if you look at this equation right here, where you've got A plus B produces C and D. You see that arrow there? It's only going one direction, right? Because A and B will produce C and D. And you start off with these guys here initially. Initially, you have 0 of these guys. And as the reaction goes, your amount of reactants goes down. Your amount of products goes up. Eventually, your amount of reactants will go to 0, and you'll have 100% product, right? Well, sorry, it's a bunch of baloney. I am a liar. To teach chemistry, we have to lie every once in a while. And I don't feel bad about it either. All right? These reactions don't work in one direction, one-way street. As with the body, there is an equilibrium. So if you start off with 100% reactants and 0 products, right, which is kind of how we start off with, we mix A and B together, what happens is because there's a lot of reactants and 0 products, things move from a high concentration to a low concentration. All right? So this reaction is going to go all the way to the end. So there's 100% product and 0% reactant. But what will happen is this arrow will flip. And then, because you see, we started off with 100% product and 0%, or sorry, 100% reactant, 0% product. The reaction goes in the opposite direction. But then what happens is, goes like this until there is a happy medium. Now, is it 50-50? No. 70-30? I don't know. 60-40? Whatever it is, every reaction is different. But every reaction will find an equilibrium. So in actual terms, the arrows will start to look like this. And that will happen there towards the end of this. I just wanted to throw that in there. Equilibrium. We're going to get there. Okay? But what I want you guys to see from this is acid. In this case here, this is a base. Now, an acid is a hydrogen producer. What's my hydrogen producer on this side? Well, it's this one right here. What if I flip the reaction completely over? So we only look at these guys here, and now the reaction is going to go this way. Where's my hydrogen producer on this side? So this is my acid. And what's going to accept a proton on this side, or what can accept a proton, is this guy here, so it must be my base. So on this side here, we have an acid. Here we have a base. On this side here, you also have an acid, but we call it the conjugate acid. And over here, we also have a base. We'll get more into that I have some questions there. What do we got here? Conjugate acid base. So I will ask you what is, and even on the assignment, what's the conjugate acid base pair? What is going on here? Where's my acids? Where are my bases? Not just on one side anymore, but on the other. So if you look here, ammonia is a weak base that forms ammonium ions and hydroxide and water. So you look at this right here. Here's my ammonia. It's a weak base. And here is water. Just water. Now you think what's happening here. If you can't see what's happening here, go over to the other side. So what happened here now? So this guy here lost a hydrogen, and this guy here gained a hydrogen. So so basically a hydrogen jumped from here onto here. So whatever's producing the hydrogen, bang, acid. So right there, water can be an acid or it can be a base. So water can give hydrogens or accept them. So here in this case here, a hydrogen jumped from the water over to the ammonia. This would be my acid, and this is my base. Let's flip it over. Where's my hydrogen producer? If I need hydrogens, where are they going to come from? Hydrogens will never come from a hydroxide. This is a stable, you're not going to break that easily. So where are my hydrogens going to come from? Over here. So this guy here is my conjugate acid. And if a reaction is going to happen between these two, what's going to happen here? Well, this guy here is going to accept a hydrogen. So therefore, that's my conjugate base. So what I want you guys to take from this, who is donating the hydrogens? Those are going to be my acids, whether it's acid on this side or conjugate acid on this side. Who is accepting the hydrogens? Those will be my bases and my conjugate base. And have a look here. Ammonia is a base on this side, but it will always be the opposite on the other side. Here's my water. It's an acid. Here's what's left of my water. It's a base. So just a little thing there to conjugate acid base pairs. Here I have the ammonium and the ammonia, water, and these guys here. Acid, base, conjugate acid, conjugate base. Let's have a look at this one. Identify the base in the following reaction and the compound's conjugate acid. So you have a look here. And if you can't see what's happening, break it down. So here I've got, well, this was phosphoric acid, but it's missing a hydrogen already. Hi, Shaylin. Can you guys hear?
We can hear you, but you can't hear us.
All right, sorry, I had my, sorry, I guess I'm just yakking. So, yeah, sorry, I totally had my mute on. I just like to hear myself. Sorry, what do you guys got?
I have a quick question.
Yeah.
You said the base is the one that accepts the hydrogen and then the acid gives it away. How do you know which is when, like, the water is going to be the base of the acid?
Excellent question, eh? Excellent question. Now, let's go back to this one. Now, this is the reaction I'm going to give you. I'll give it to you in words, or I'll give it to you in chemistry. So you're looking at this going, okay, it's hydrochloric acid and water. All right. What do acids do? Produce hydrogen. And you just judge, okay, I don't see what's going on. But look on this side here will tell you where everything is going. So you see here that H3O plus, well, what happened? You got to figure it out. Here's my water. Obviously, this hydrogen jumped over here. And that just left us with here. So what you got to do is you look at your chemical reaction. And that's how you do it. You got to figure out where the hydrogens are going. Like if you see this one here, what's going on with all of this? Well, I got my ammonia, I got my water. What happened here? Well, I've only got this left of my water, and I've got this, which kind of looks like this guy over here, but it's got an extra hydrogen. So that means that one of the hydrogens there from the water must have jumped over here. Okay? Once you guys see these and do these a couple times, they become like cake. Hopefully there, Shaylin, that worked for you. But let's have a look at this one right here. Let's try and figure this one out. So here I've got this one hydrogen short of phosphoric acid, which should have been H3PO4. But this one here is H2PO4 negative. So this is an ion. And aqueous means in solution. All right, so they put it into water, made a solution out of it, and I got water here, okay. And then you have a look here. Here I got HPO4, so I lost the hydrogen from this guy. Where did the hydrogen, and you also see there that because I lost the hydrogen, I'm now 2 negative, because hydrogens are 1 plus. If I lose 1 plus, then it becomes 2 negative. And then I have my H3O plus over here, which was water. So you're just going to have to see that one of these hydrogens jumped over. Okay, so if one of these hydrogens jumped, that means that this guy here is my acid. Hydrogen producer.
Will we always be given the products?
Oh, yeah. I'll give you the chemical equation with the reactants and the products, sure. I'll give it to you in chemistry like this, or I'll sometimes give it to you in English, which is more of a pain in the butt because then you got to figure out, okay, hydrogen, sodium phosphate, sodium is +1, phosphate is -3, crisscross. You guys remember that stuff, right? But you have a look here. An acid is a hydrogen producer. Well, this is my hydrogen, so this is an acid. And where did that hydrogen go? It went on to here, so this has got to be my base. And an easy way to do this is if this is my acid, then this is my base. That's how they work. If this is my base, then this has to be my acid. And it kind of makes sense because if I flip the formula around, so if these guys here are my reactants, because they are, because look at my double arrow. Here I have HPO4, here I have H3O+. Which is going to be my hydrogen producer if I need hydrogens? Well, it's going to be this one here. This is going to be my conjugate acid. This will be my conjugate base. Okay? So that's what we're looking at. Acid, base. Conjugate acid, conjugate base. Try a couple of those there. Just to let you know, though, as well, I have... oh, that's your assignment. I've updated the formula sheet. Okay, week 2 and week 3. We use a lot of this one. Also, we use it all the time, so it's in there. But you'll see here that these formulas, that's for acids and bases. Not too bad. I'll show you how to use those. And I also included... is this here? Oh, here are the answers to the questions in the syllabus. And this one here I included. It's from my own little library. Please don't do them all. Like, if you have that much free time, go for it. But try some of these. Like, the answers are all down below. You know, they're just, you know, nitric acid, hydrochloric acid, sulfuric acid. This one here is sulfurous acid, acetic acid, that's vinegar right there. Try some of them. You can name them. At least have a look at them there. Here it asks you for the chemical formula. All right. Bronsted-Lowry is just asking there to label the acid base, conjugate base. Same. It doesn't even use the word conjugate here. But just as long as you know, because you see you have a double arrow, and that's where we're going. We're going into, there really is no products or reactants anymore. It all depends on which side of the mirror you're looking at. There's more stuff there. Again, more conjugate base pairs. You guys make the equation. And we'll get into pH there later on today. Okay, so there's lots of stuff there for you guys to do, and the answers are all included in there as well. Did I just finish that one? There we go. What do we got here? Which are the two Bronsted-Lowry acids? Proton. So here we're only looking for the acid and the conjugate acid. So look for your proton donors. Well, here I got water. Water can be an acid, but in this case, is it going to be? No. Here I got sulfuric acid, hydrogen sulfide. Okay, and so that's what. Sorry, hydrosulfuric acid. Oh, losing my mind. I just came off a 2-hour meeting there with another class, and it's a good one. So you have a look here. There's your hydrogen, and now flip it around. Which one is going to be the hydrogen giver if we need it? This guy right here, and that's what we got. This one here I don't really care too much about. I don't even think, I just throw it in there just to confuse you. But the Lewis acid base definition, a base is an electron pair donor. An acid is an electron pair donor. I don't even think there's a question on there about Lewis acids and these kinds of things. But you'll see here that what's happening is an acid can accept a pair of electrons. And don't even worry about that one. But here's a nice little summary of acids and bases. The Lewis one there I'm not too worried about. I'm more worried about the Arrhenius and the Bronsted-Lowry. Because these guys here, like the Arrhenius, this is what hydrogen, and bases are hydroxide. That's it. All right? But the Bronsted-Lowry, hydrogen producer, hydrogen acceptor. Okay? Those are the two there that I really want you to know. And because basically where you guys are going in nursing, you guys aren't going to be worried about the Lewis definition of an acid when you're dealing with acidosis of the blood or something like this. All right? It's hydrogens that are the problem. All right? Or it's bases, hydroxide, OH, that's the problem. That's what you need to know for where y'all are going. So don't worry about the Lewis definition of an acid, but know that hydrogens are the end-all and be-all. Just some reactions there. I might give you one here or there. You know, acids react with metals. So here we've got hydrochloric acid. And I might give this to you. It's actually more difficult than it sounds. If I give you this question in English with words and ask you to transpose it into chemistry, which one is it? It's not as easy as it sounds, because hydrochloric acid plus magnesium produces the salt. Now, what would the salt be? We'll get into what a salt is. A salt is an ionic compound. Oh, I thought there was a kid sneaking around. But here we have an acid, a metal, produces the salt. Now, we're all used to table salt, sodium chloride. Yum, yum, yum. It's good for us. Not in large amounts. But in chemistry, a salt is any type of an ionic compound. Now, what's an ionic compound? It's a metal plus and a non-metal minus. So you look here, I got magnesium chloride. Magnesium is 2 plus, chlorine is 1 minus, comes from group 7. Crisscross, you get MgCl2. If you guys are having issues with these, let me know. I have stuff there that I can give you, okay? Because we'll be all over that like a duck on a June bug, as my grandmother would say. And then hydrogen. So if you look, if I just gave you the, if I say hydrochloric acid plus magnesium produces magnesium chloride and hydrogen gas, and ask you to make all these, it's not easy, okay? So just be careful, all right? I might give it to you in English or the chemistry, and then afterwards, you may have to balance it, all right? But I'll let you guys know about all that. Acids there can react with bases, which we'll get into. That's like half of the PowerPoint. And please make a note somewhere. An acid-base reaction is a double displacement reaction. All acid-base reactions are double displacement. Remember that one? And all acid-base reactions produce two things, and two things only. The water and the salt. Now in this case here, I've got hydrochloric acid and calcium hydroxide produces calcium chloride and water. Okay, acid-base reaction, double displacement. Okay, and you guys can see the reactions here. Acids react with metal oxides. Here we have sodium oxide. Okay, and here we've got salt and water again, but this isn't an acid-base reaction. Okay, acids react with metal carbonates. So a carbonate, when you guys get into blood chemistry, we'll get into buffers there later there in the PowerPoint. Your blood has a buffer in it. Your pH of your blood is around 7.4. And I don't mean around, I mean pretty much, because if it varies anything significantly, you get into severe trouble. So your body, I just love how the body has evolved, man. It's just incredible. You breathe in your oxygen, right? And there's two breathing parts, right? There's external respiration, which carries the oxygen to your big toe, and also it gets rid of the carbon dioxide, which just came from your big toe. So that happens here in your lungs, external. And then you have internal respiration, which is the gas exchange going on in your big toe via the bloodstream. And by the time the oxygen gets to your big toe, there's a huge concentration of oxygen in the blood, jumps off into the toe, which has a huge concentration of carbon dioxide, okay, which dumps that off into the blood. And carbon dioxide, your body changes it into bicarbonate ions, which is CO3, and acts as kind of a buffer. It's able to absorb and keep the pH, the amount of hydrogens in the blood at relatively the same. And as the carbonates travel up, sorry, I'm going the wrong way, back to your lungs, It's keeping the blood buffered at the same pH. We'll get there. I got a couple slides on that one. All right, so these are your carbonates, and they produce these guys here. All right, with an acid. What have we got here now? Bases. Now this word here, I really like it. Okay, amphoteric. Like water. Can act like a base. Can act like an acid. Okay, that one there, I like that word. It can go both sides. It can act like an acid or base. Okay, amphoteric. These guys here, we'll get into what a strong base really is, but sodium hydroxide, potassium hydroxide, about as strong as you're going to get, man. These things are caustic, and they will burn just like an acid. Okay, and but you got bases, metal, and water, and you get these guys here, and that's sodium aluminum hydroxide, massive salt. Wouldn't worry too much about those. I may ask you one of them there just to irritate you, but that's not going to be a focus. Where we're going to focus on is on pretty much everything else here. Electrolytes. Now, when you're out swimming, like before I answer that question, if I have a beaker of pure distilled water and I hook up 2 electrodes, like just the whole idea that I go take my kids swimming in Kempenfelt Bay there in the summertime, and if there's a storm coming, right, Mama always said, get everyone out of the pool, right? Because electricity hits the water, it'll come right for you, and you'll get electrocuted. But not so. If you have a beaker of distilled water, only water, hook up 2 electrodes to a battery, electricity will not flow through that beaker. Why? Then why did Mama say get out of the water, man? I could have had an extra 15 minutes in the water. Well, that's because the water in Kempenfelt Bay is full of salts, dirt, this and that, and all these different types of ions. And what is electricity? Just electrons. They're negative. They need positive ions there to carry them through. So if you have a look here, I don't know if you guys can see or not, but I've got pure water hooked up to an electrode. No bulbs, no lights, no nothing. Because pure water is just molecules of water, no ions, so it will not conduct electricity. Okay, I can put sugar, a little bit of sugar or something in here. Okay, and sugar will kind of make ions. Not really, but it will. So therefore now the light bulb will come on a little bit because there are a small amount of ions in solution. If I dump salt water, and make salt water out of this thing will just carry a current like a copper wire, which is why we get out of the water there. And Mama was right. Mama's always right. Don't mess with Mama. All right. Electrolytes and non-electrolyte practice. Which compound will not dissociate in water? Now I'm setting you up for something here. When you put hydrochloric acid into water, it breaks into sodium ions and chloride ions, 100%. If I put potassium bromide, ionic salt, into water, it will break into its ions. Potassium plus, bromine negative, and they're in solution. Sodium hydroxide, very strong base. 100% breakage into sodium ions and hydroxide ions. So these 3 here have 100% breakage. And that's what I'm going to call it. It's not really a great word, but if a compound has 100% breakage when you're making the solution, that thing has electrolytes in it, and that thing will conduct water like a copper wire. Some molecules do not break. And here we have methanol, aka washer fluid. It doesn't break. So when I mix methanol into water, you buy this there at Canadian Tire, you're getting that. It doesn't break at all. So if I put this into water, it's not going to conduct electricity because there's no ions in it. Okay? So D will not dissociate, will not break. Electrolytes. Yeah, you know what I mean? The most famous commercial there is Gatorade. And don't buy Gatorade. Please, Gatorade is junk. It's a waste of time, waste of money. $4 for a bottle of salt water with a little bit of sugar in it. You can make your own. To go and buy Kool-Aid, just put in 20% of the sugar that you would normally put into Kool-Aid, and then add about the same amount of salt, table salt, into your Kool-Aid. Mix it all together, there's your Gatorade, and you just saved. Like if you buy Gatorade twice a week, those things are like $4 or $5 for a bottle. So, but anyway, those are your electrolytes. And electrolytes are just ions in solution, and we need them. Like you guys have already done muscle there in bio. You guys would have done the sodium-potassium pump. That's how muscles fire. That's how nerves fire. You have ions on one side of a membrane with a charge, and you've got sodium ions there on the inside with another charge. You got potassium and sodium. And when a muscle fires, that pressure gradient flips. So now the potassium are on the inside and the sodium's on the outside. And that's a muscle fires. And in order for that muscle to refire, you have to realign them again. So that's where the ATP comes in line. All right. I know this for a fact. I was in the Middle East there, and my very first summer, I woke up one morning, and like I'm trained here in Canada not to eat salt, because salt is bad for you. Salt can cause heart attacks, these kinds of things, right? But when I was over there, I spent, 15 years over there in the Persian Gulf, the Arabian Gulf, and you learn to put salt on your food because you need that salt to survive. Because when it's 52 degrees out there, and I tell you it is, you can actually see salt crystals on your hand. The salt evolves out of your skin, so you lose that salt. And if you don't have that salt in your system, your muscles don't fire. And I woke up one morning ready to go to work, and I couldn't move. Yeah, they called an ambulance, loaded me up, hooked me up with 2 saltwater bags. I had 2 IVs, one in each arm, and within an hour I was up and ready to go again. So you need those ions, okay? So that's electrolytes and non-electrolytes. What do we got here? Acids, bases, and salts are electrolytes because they produce ions in water. Non-electrolytes like the methanol, okay? So here are some examples there of real non-electrolytes there. Now we're getting into the good stuff. Ionization. Remember that I was talking about breakage? Well, instead of breakage for acids, let's call it ionization. Because when you put an acid into water, acid is a hydrogen producer. Well, what separates a dangerous acid from a non-dangerous acid is the amount of hydrogen it produces. That's it. So sulfuric acid, battery acid will go through your hand. And then you have vinegar. They're both acids, but one of them there is a dangerous one. And the only reason sulfuric acid is dangerous is the amount of hydrogen that it produces. And so here I have hydrochloric acid and water, and you'll see there that it breaks. So that when you make your solution of hydrochloric acid and water, this is what it looks like. It's H3O plus and Cl minus. And let's say I had 5 of these guys and 5 of these guys. How many of these guys am I going to make? Well, I've got 5 water molecules. I have 5 of these hydrogens, so 5 of these. So all of these guys are going to go here. So I'm going to have 5 of these guys and then 5 of these guys. I know it seems kind of rudimentary, but give me a sec. I'm going somewhere with it. Now, And you have a look here at this one. Here I got phosphoric acid. Whoa. This one here is pretty dangerous as well. Why? Because it has the potential to throw out 3 hydrogens every single molecule. See, like hydrochloric acid here, it can only throw out 1 hydrogen. But phosphoric acid, it has the ability to throw out 3 at one shot. And you see here, so one of these hydrogens went on to here. So I have H3O plus. And now, what if I added another water here? One of these hydrogens could go on to this water. And you see how this could keep going on. So that's why this stuff here can be quite dangerous. Here we've got weak bases. All right. And as we've seen this reaction there, okay. I want to come back to this one when we get into what a weak acid is. But for acids, the process of dissociating and breaking up into water, we're calling it a new word, ionization. Okay. What we got here now, this is going back into the light bulb situation when acids have 100% breakup, 100% ionization. So when you put the acid into water, 100% of what you put into it is now broken up. So what you have basically is the maximum amount of hydrogen that this acid can produce. That's a strong acid. That's a dangerous acid. When you have maximum hydrogen, maximum breakage, maximum ionization, only strong acids or strong bases will dissociate 100%. So bases will work the same way, we just call it a different word. A strong base, NaOH, you put it into water, you'll get 100% breakup, 100% dissociation, so you'll have maximum hydroxide. That's what makes a dangerous base. Because hydrogen in great quantities is dangerous. Hydroxide in great quantities is dangerous. Okay? A weak acid or a weak base, like vinegar being a weak acid, all right? Great on your French fries, that kind of thing, a tomato. Even the whole idea there that when you had heartburn there, your mom would give you a glass of milk. And milk is even an acid. But milk has all these, it's colloid, it has all these proteins and everything in it that kind of push the acid down. But weak acids and weak bases, they do not break 100%. And you'll see here, like this is acetic acid, vinegar. And up here we have hydrochloric acid. I'll zoom in a bit. So you put in hydrochloric acid into water and you'll look. These are my hydronium ions, H3O+. I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. These are my chloride ions. So there are no species in there where the hydrogen and the chlorine are stay together. They 100% break. So 100% hydrogen, that's dangerous. But let's have a look here. I think I'm screwing up my PowerPoint here, but I'll get that back. Here I have acetic acid, which is vinegar. These are my acetic acids. Look at them. They haven't broken. The majority of them have not. The hydrogen hasn't been stripped away. But some of them have. Like this one right here. This one was this guy, but a hydrogen broke off. So, I don't know, what do we have? 20 of these guys and only 2 have broken? So you see the amount of hydrogen that's here is considerably smaller. How small? We'll deal with that next week. But you see that these guys here are not dangerous. Well, don't put vinegar in your eye. All right? But hydrogens make it dangerous. The more hydrogens, strong, dangerous. The more hydroxide, strong bases, strong acids. These guys here, weak acids, weak bases. And I'm going to harp on this huge over the next hour. Okay? Oh God, next hour? Come on, Ian, you can finish it up faster than that. Let me put this guy back here. Okay, so strong acids, strong bases, 100% ionization or 100% dissociation. Weak acids, weak bases. See, I put 50% here, but it ain't. I say 50-50 because it's less than 100. It could be 90-10, could be 80-20, but it's somewhere less than 100 and a lot less than 100. So weak acids, 50-50 ionization. Weak bases, 50-50 dissociation. That's what makes them weak and not so dangerous. Please don't get confused with these 4 words. These 2 words here are pretty vague, and I want you to know that it's vague. A dilute solution just means that it's not concentrated. It's kind of a weak solution, you know. If I put 1 tablespoon of sugar into a glass of water, okay, it's a dilute concentration. But if I add 5 more scoops of sugar into that same glass, now I've got a concentrated solution. That's all it means. Like, it's just talking about the amount, right? And there's your strong acid and strong base. And that only comes from its ability to break ionization and dissociation. And I think I have a list of strong acids and strong bases that I'd like you to know. I'm not going to harp on it, but there's probably 3 or 4 of each. Excuse me. Got a tickle in my throat and I'm going to feel like I'm going to cry. But there is a couple of them there that you should know, and I'll let you know what they are. Next one there, a weak acid or base. This only comes from its ability only partially ionize or dissociate, okay? Like ammonia or acetic acid vinegar. And the example I use is, have a look at this one. See if you can get this one. Hydrochloric acid is a strong acid sold concentrated in 12 molar bottles. Oh, I've seen this stuff, man. It's nasty. It pours out like syrup. It's so thick and so bad. Such a bad smell to it, too. So, hydrochloric acid is a strong acid. What does strong acid mean? 100%. It's sold in a very concentrated bottle, 12 molar. And what does molar mean? 12 moles per liter. All right? Very, very strong. So it's sold in 12 molar bottles. It can be diluted to a dilute 0.1 molar solution. You know, using that formula M1V1 is equal to M2V2, you can create a dilute solution from this. But a dilute solution of 0.1 molar hydrochloric acid is still a strong acid. It's just dilute because there's not enough in it, but hydrochloric acid will always break. I will come back to that later on, okay? So don't get these 4 terms there confused. Here I'm just going into strong acids again. In strong acids, such as hydrochloric acid, nearly all the acid ionizes. So you see here, that's what's going on in a strong acid. And do you notice a strong acid? There is no arrow going back. In this case here, it is a one-way street. That's why strong acids and strong bases are so dangerous, because there is no equilibrium for these guys here. These guys here, you pour hydrochloric acid into water, you are getting this.
Ian?
Yes, what you got? Hello?
There's a question in chat about how this product would be shipped.
How the what?
There's a question in the chat about how that solution would be shipped.
You used to see the bottle on it. The bottle, it's got a handle on it like this. It's all glass, right? It's all like, I think the bottle is just impeccable. Glass bottle, and they you grab it by the bottom, you grab it by the top. It's heavy duty glass and heavy duty top on it. Like the bottle itself probably weighs about 8 pounds. Like, it's massive. And yeah, it's dangerous stuff, man. It's got to be labeled. You guys are familiar, maybe not so familiar, but I'm sure the word MSDS sheets will mean something to you. Material Safety SATA, Material MSDS, Material Safety Data Sheets. Say that 5 times. All this stuff, all these dangerous chemicals, they are mucho bueno protected. So that's how this stuff is stored and transported. And yeah, bad stuff, man. I hope that answered your question. Is that what you were looking for? Okay, good. What have we got here now? Weak acids. Look at our arrow now. So not 100%, maybe 50-50, 70-30. That's what we're looking at. So strong acids, 100% over to here. Weak acids, there's going to be some on both sides now. All right, so we've got some on this side. We've got some over here. It's a 50-50. That's what the definition of a weak acid or a weak base is that there is an equilibrium. Is it 50-50? Definitely not. Somewhere in there. But next week we'll be able to calculate all this stuff. Here's an idea there of a strong base. Again, look at the arrow. Choom. Only one way. So 100% dissociation. And here we have a weak base. Have a look at my arrows. Somewhere in between there, there's an equilibrium. It finds itself. And we don't have 100% breakage. So that was weak acid, strong acid, which kind of correlates to a weak base and a strong base. It all depends on the amount of breakage. That's it. And I'm sorry if I harped on it enough times. If you got that, then the questions there the next 2 weeks should be all right. As long as you can remember and be able to recognize a strong acid or a strong base as opposed to a weak acid and a weak base. Okay. Salts. They are, in science there, we use these. They're basically ionic compounds, metal, non-metal. You'll see that there, M+, X-. Okay. The example there, hydrochloric acid and sodium hydroxide produces sodium chloride and agua. All right. Salts are ionic compounds composed of a cation, usually a metal, and an anion. Okay. Salts are usually crystal. All right. Ionic compounds they're insanely stable. I think the melting point of salt is 800 degrees Celsius. Like, it's just ridiculous how stable these ionic compounds are. Let's have a look here. This is what I'm talking about now. These ones here aren't going to be easy, but this is any test that I give you or assignment is all open book anyway. So you have a look here. What salt forms from the reaction of magnesium hydroxide and sulfuric acid? Well, you don't have to memorize magnesium hydroxide or sulfuric acid. You know, you could find them up, or you could just make them. And so magnesium hydroxide. Hopefully you guys can remember how to do these. If you need more work, ask me and I could send you guys pages on this stuff. Magnesium is in group 2, so it's 2+. Hydroxide is -1. It's a polyatomic ion. Crisscross. The 1 that was up here goes down. The +2 that was over here goes down. So you got Mg bracket O2, OH bracket 2. Sulfuric acid. There it is. And now this is a acid-base reaction. You got what are the only 2 products of an acid-base reaction? Water and a salt. So you could actually put H2O plus. Now what would the salt be? The salt will be here and here. And then you'd balance it and do what the question asks you. What salt forms? It's this guy here. What salt forms from the reaction of aluminum oxide and hydrobromic acid. Well, there's your aluminum hydroxide, or sorry, aluminum oxide and hydrobromic acid. What would be acid base, water salt? You guys can see how that one works, okay? So I like those questions because they pull on everything there from last semester. All right, it's incorporating acids and bases. You got to know what the products are of an acid-base reaction. You got to remember that the oxidation number for magnesium is +2. And I don't know if you guys have something like this. I can give it to you. Let me find it and I'll show it to you. I made my own periodic table that has basically everything you ever wanted. So yeah, maybe I will send it to you. I think you guys would appreciate that. Let me get back to that, and it has all the oxidation numbers of everything there. I'll show it to you there. I'll find it there before the end of the lecture, and I'll post it anyway. What do we got here? Which two will dissociate? Think ionic salt or strong base. Because dissociate doesn't apply to an acid, right? What's the word that only applies to acid? Ionize. So, which two will dissociate? Well, that's methanol. That's organic. That's next. That's after spring break. So that's no good. That is an acid. That only ionizes. So here's my ionic salt. And here's my base. Okay. Which three will ionize when placed in water? Think strong acid. Okay. And tricky. This one here, sulfurous. It's not a strong acid. And you could find that out. Okay. This is nitric, strong. Hydrochloric, strong. Sulfuric, strong. Know those. Those three right there. Maybe there might be one or two other, but you'll have to be able to recognize, whoa, those are strong acids. That's 100% dissociation, because that will play into effect of what we're doing. Okay. A solution is tested with the conductivity apparatus, and the light bulb did not light. Oh no. Which of the following is likely? Okay. The beaker contained only water. What would happen if the beaker contained water and calcium chloride? The light bulb would be bright. You think about this. If I put calcium chloride into solution, how many ions? If I put this one right here, you see, CaCl2. There are 3 atoms in this banana. 1 calcium and 2 chlorines. If I put this compound into water, what would happen to it? It would break into calcium, 1 chlorine, and another chlorine. It would break into 3 ions. So you see, no wonder that light bulb is on fire. B, the beaker contains agua and sugar. Sugar is not a great ion maker. It will kind of do something, so the light bulb will come on very little. Getting into dissociation of electrolytes. You guys will remember there last week the whole idea of putting sugar into water and the water, oxygen being a very aggressive atom. Okay, we'll go right after the lasagna on your pan, and just the whole idea of clustering around, pulling it away from the edge of the pan, and then spreading out. That's how this thing goes. Okay. Salts dissociate into at least 2 ions. Have a look at this. See how this one tickles you here. A 1 molar solution of sodium chloride. So 1 mole per liter. 1 molar solution of sodium chloride will produce 2 molar solution of ions. Just going back into that same what I was talking. Remember the barium chloride? I think it was, calcium chloride. If I had a 1 molar solution of calcium chloride, what would be my molarity of just the ions? Sorry if you can see that. 3. Let's go back here. If I have a 1 molar solution of sodium chloride, if I put that into solution, 100% break, I'm going to have sodium and chlorine, so I'm going to have 2. So I'm going to have 2 moles of ions in solution. Here I have my calcium chloride again. So 1 molar solution, this will break into 3 ions, which will triple your molarity of ions. And you think about that, what that would do there to a light bulb, right? The more ions, the more bright this thing's going to shine. What is the concentration of a chloride ion in a 2 molar solution of calcium chloride? I love this question. I love it. So I have a 2 molar solution of calcium chloride. Okay? 2 moles per liter. I put this into solution. What is my concentration of only chloride? Well, if this guy breaks, I have 3 atoms in one of these guys. And these 3 atoms will, this is a 2 molar solution, but 1 atom, the other, and the other. So if this is all 2 molar, that means I've got 2 moles of this, 2 moles of this, and 2 moles of this, which means that we will have a 4 molar solution. I think there's a question on the quiz, or was it on the assignment or somewhere like that. If you're having issues with that, come and see me. The whole solution is 2 molar. So I have 2 moles of these guys. But once I put these guys into water, they break up into their 3 atoms, right? So if I had 2 moles of these guys, I got 2 moles of these, 2 moles of these. So now you have 4 moles, 4 molar solution of that. Let me go quickly. Soap. Soap more than ever is more important. Now in this pandemic age. I forget the song you're supposed to sing. Little Red, I forget the song you're supposed to sing while you wash your hands. But soaps are indeed salts. And what makes soap so incredible is they have this non-polar organic chain of carbon atoms at one end. So basically they have a non-polar end. Like if you go back to polarity, here I have this polar end. Why is it polar? Because you got oxygens here. Who's the big? Fluorine is the biggest boss. Oxygen is number 2. All right? And it likes to hoard atoms. So this side here is going to be polar. There's going to be a charge here. But then you have this long chain of just carbons and hydrogens that is non-polar. Who's the big boss here? Well, the carbons, but they're kind of they're all protected by, we'll get more into that there when we get into week 8. But you've got these non-polar chains and these polar ends. And if you just put soap on your hands, it's not doing anything. You need the soap to be dissolved in water because water is polar. And like if you mix water, if you just put water on your hands, it doesn't do anything either because the grease on your hands is grease and grease is non-polar. Water is polar, grease non-polar, then they'll mix. So you can put all the water you want on your hands, but you're not getting any clean hands. That's why we have soap. Soap has both of these. So what happens is you have soap and you have water. If you just have a bar of soap here on your hand, sorry, I'm trying to do this in front of the camera. If you have a bar of soap on your hand and you just put your hand under water with the soap in your hand, nothing's going to happen. What you got to do is you got to get moving. You got to get the soap and the water all mixed together because what happens is now this guy here will stay with the water, but this part here will embed itself in the oils on your hands. So you've got the long chain inside the oils on the top of your hand surface and the polar end in the water. And because you're doing this now, you're just breaking everything apart. All the oil that was on your hands is now in little bits and pieces because of this. And oil isn't water soluble, but when you break it up into these little pieces, it'll go down the sink. So that's a little bit of soap chemistry. I think I have one more slide here. It just basically details the same thing of what I'm just talking about. There's your non-polar polar end, and you see it breaks the dirt up into little pieces. Have a look at that, and that's how she goes. How we doing for that? Are there any questions there that you guys see any issues with? If you do, let me know or email me there later, whatever you guys think, okay? Holy man, that's sun. That's a good one.
Ian?
Yes, what do we got?
Can I ask for clarification on the dissociation of like bases and salt?
Sure.
What's really happening there?
Okay, so this is Alexander. How's it going? So, where are we here? So, the whole idea of breakage, you know, when you put an acid or a base or a salt into water, right? They'll break. Now, a strong acid, a strong base, they'll break 100%. A weak acid, a weak base, they'll break 50%. But what the whole idea of breakage, there's two words there that you need to know. Acids have breakage, but we call it ionization or ionize. They make hydrogen. They make ions. Okay? And bases and salts, they dissociate. How are we doing? Talk to me, Alexander.
How are we supposed to like identify what is going to be like a strong or a weak like acid or base?
Oh, that's it. I just saying there, hydrochloric acid, bang. Sulfuric acid, bang. Nitric acid, bang. There was a slide there. Where did that one go? I think there might be another slide coming up. Where did that go? That's non-electrolytes. It's in there somewhere. I'll see if I can find it. But first thing, be able to differentiate an acid from a base from a salt. So an acid, hydrogen producer. A base will be a hydroxide producer. Okay? And a salt is just an ionic compound, like magnesium chloride or sodium oxide, metal, non-metal. Those are salts. Now, acids you can further break down. Acids ionize. They break into 100% strong acids or 50-50. They're weak. And bases will do the same, but they dissociate. So talk to me. What do you got?
So, like, on the right side of the chemical equation, like, when we're looking at these, like, it'll just, like, say,
no.
Like, it'll just have, like, an hydrogen or a hydroxide.
You will have to know if it's a strong acid or a strong base. And sometimes I may tell you but if it's a strong acid, it's only going to have one arrow here, and it's going one way, and it's breaking up 100%. So hydrochloric acid, don't worry so much about weak stuff there this week. We're going to deal with that more next week. Today, I just want to introduce to you guys strong acids and strong bases kind of a thing, and 100% as opposed to 50%, which was the weak acids and weak bases we'll get into more there next week.
Okay, I think I should be fine after I do some questions.
All right, and email me for sure. All right?
Okay.
And there'll be time at the end of class here if you guys want to shoot it up, and let's go. Where are we here? Good question, though. It's not easy. How do you identify? How do you know if it's a strong acid? How do you know if it's strong? How do you know? And you just got to dig in and try these out a couple times. And if a question doesn't work, shoot me an email. pH. Welcome to it. pH just stands for the potential for hydrogen. And you have a look here. This is our pH scale. And the pH scale, I've added some formulas here, which I've included throughout a couple times there. But this is a pH scale, and it goes from 0 to 14. It's based on a logarithmic scale. It's really not that important for where we're going, okay? So pH values will only be between zip and 14. And in the middle is 7. This is neutral, where the amount of hydrogen is equal to the amount of hydroxide. I've tried to make these guys, I guess that guy should be over here, I tried to make them kind of the same. Okay, so at 7, the amount of hydrogen in the solution is equal to the amount of hydroxide in solution. So they're neutral, they have a pH of 7. Water, distilled water, has a pH of 7. But let's just look at anything under 7. And you'll see here that as we go down the scale, the amount of hydrogen exponentially increases by a factor of 10 every jump you go. So 6 has 10 times more hydrogen than 7. And as we go down the scale, our hydrogen increases. Where do you think the dangerous acids are? Right in here. Stomach acid is about 2. Bad stuff. Coca-Cola, funny enough, is about 2.2. Yeah, throw a quarter into a glass of Coca-Cola and leave it there for a week, see what happens. Strong acids are down here. These guys here will have 100% breakup. The stronger the acid, the more breakup, more ionization it has. All right? Inversely, though, have a look. Now we're into the basic region where, in this case, there's more hydroxide than there is hydrogen. Now, you have a strong acid over here. Does that mean that there's no hydroxide in the solution? There is, but it's just very small in comparison to this. And if you go over to the far right, bases that are in the 13-14 range, now you're talking bad news. Bad news over here because the amount of hydroxide is so much more than the amount of hydrogen. There is a little bit of H+ in a solution that has a pH of 13, but we're talking maybe 100 billion less than these guys here. Like, every one of these is a jump of 10. So if a solution has a pH of 9 and then a solution has a pH of 10, I know it looks like it's one jump, but it's actually a factor of 10. So 10 has 10 times more hydrogen than 9, a pH of 9. A solution with a pH of 11 has 10 more than the solution with pH of 10. It has 100 times more hydroxide than the solution has with a pH of 9. So these are all by a factor of 10. All right. Tomatoes are in here somewhere. Vinegar is in here somewhere. Milk is 6.5. Blood is around 7.4. And it don't deviate that much. These are the formulas there that we're going to be using. Funny enough, while I got this slide open, when you have like, that's why I included both of these. In the, for the strongly basic solutions, you have a huge hydroxide concentration and a very little hydrogen concentration. For a pH of 7, you have exactly the same amount of hydrogen as you do hydroxide. For a pH of 1, you have a huge amount of hydrogen and a wee little amount of hydroxide. But it doesn't matter. If I multiply the amount of hydrogen here for a pH of 1 times the amount of hydroxide that I have, I'm always going to get this number. If a pH of 7, if I multiply this hydrogen times the amount of hydroxide, I'll always get this number. This is one of those constants of the universe that for whatever solution I have, for whatever pH I have, if I multiply the amount of hydrogen, hydronium, H3O+, by the concentration of hydroxide, so concentration of H plus times the concentration of hydroxide, I always get this number. All right, so, and we call this, you're going to start to see this K. What K means in chemistry, it just means one of these constants of the universe. It's KW. It means the constant for water. Okay? And you're going to, by the end of this course, you're going to have about 4 or 5 more Ks. But right now, the K of water is equal to the concentration of hydrogen times the concentration of hydroxide is equal to 1 times 10 to the negative 14. Why is that important? We'll get there. Here's the formula there for pH. Don't worry, it's all in, we're going to go over this again. pH is equal to the negative log of the hydrogen concentration. The inverse of this formula, if we flip it on its head, the hydrogen concentration is equal 10 to the negative pH, the exponent negative pH. I'll show you guys how to use these. pH plus POH is equal to 14. Yes, this is the pH scale, but there actually is a POH scale, which we're not going to get into. But there's the formula nonetheless. Okay? What do we got here? Measuring the pH of a solution. There are 3 ways there that you could do it. There's litmus paper. Okay, will turn red in the presence of an acid. Blue for base. Universal indicator is you put in a chemical there and it will go to 6 or 7 different colors, and then you can use a scale, kind of looks like a rainbow scale, and you can tell what the pH is based on the color there that the solution is producing. There's actually a really good, if you guys wanted to do some chemistry there at home, red cabbage. We actually use this in the lab. If you boil red cabbage and eat the red cabbage. I'm not a cabbage person myself, but if you take that water that's left over, that's now a natural acid-base indicator. Where if you put it into vinegar, acid, it'll go clear. If you put it into a base, it'll go pink. Interesting. pH meter. This is an instrument there. You put the probe in, it tells you the pH. Okay, very simple. And the further you go on in your career, guaranteed you will use at least 2 of these. I know we use these in there in the labs. Okay. Blood pH. In order to carry out its many functions, the pH of the blood has to be, I don't even like those numbers. I like it somewhere around 7.4. But you can see there it does not deviate much. Okay. The main reason for this is the enzymes. Enzymes are protein molecules that do stuff. Like we have amylase in our mouth. That's why if you chew a piece of white bread for 5 minutes, it actually don't swallow it. You can, kids like to do this as well. It's a good little chemistry experiment. Chew it, don't swallow it. It turns into this disgusting slurry, but after about 3 or 4 minutes, it actually starts to turn sweet because the amylase that's in your mouth starts to break down the starch molecules into the sugar. Okay, but these enzymes, they need a very specific pH range, and if it deviates out from that, and I don't want to get into protein. You guys would have covered it there last semester in bio, but amino acids grow into these chains, and because of the side groups, these chains start to fold, so you get these massive molecules that are all 3-dimensional, and they all look weird, but it's all about lock and key. This enormous protein that is formed and shaped and curved and all this, it looks like this for a reason, because it's specifically built there to go and attack a starch molecule and break it in half. So these are the point there of enzymes, and they need a specific pH. Your blood contains compounds called buffers that enable small amounts of acid and base to be absorbed without changing the pH. And it all comes there from CO2 that you breathe out and expel. On its way from the big toe out your lungs, that carbon dioxide has been converted into what's called carbonate, CO3, HCO3, which now acts as a buffer. So the body is just incredible. A waste product that's on its way out of the body. Hey, wait a second. We're going to make this stuff work for us. And from the big toe to the lungs, your body changes it into a buffer, which now maintains your blood chemistry. So allows you to live and function. It's just incredible. Love it. Love it. Love it. What is a buffer? Buffers are solutions that react with acids or bases and maintain a specific pH. So here, if I add concentrated hydrochloric acid into a salt water solution, within 2 seconds, hydrochloric acid is a strong base. This thing's going to have 100% ionization. Wham! That pH just drops right down to 2 in a second flat. Because you've just flooded it with hydrogen, and there's no place for the hydrogen to go, so all the hydrogen is just out in the solution. But our blood, if we pour the same concentrated hydrochloric acid in, look, didn't change by much, because there are buffers there with the carbonate that are able to absorb these hydrogens and take them out of solution so that they're not causing harm everywhere else. Okay? Important. When you guys get into blood there, I think you guys should be getting into blood there now, no? You guys would have done lymphatic and then blood coming up and cardiovascular. But yeah, it's a good one. Your teacher will go into more detail. How many times more acidic is a solution with a pH of 3 than a solution with a pH of 5? So let's go back. So I got a pH of 3 and a pH of 5. Well, each one of these jumps is 10 times more. So remember, going this way, you got 10 times 10. So a pH of 3 is 100 times more acidic than a pH of 5. If we're going this way for base, a pH of 11 is 100 times more basic than a pH of 9. All right. Just interesting here. You can have a look. Hey, this is great to know. And you guys being nurses and paramedics and all this, and you guys are going to be teachers for the entire community. It's why I love you guys, man. You guys are awesome for where you guys are going. And you guys will be looked upon with smiles and cheers. You guys are going to be educators. And these are just good things to know. Like milk, pH of 6.6. It's actually yellow. Who's speaking?
Let me turn on my video for you.
That's all good. I can't. I think my video is down here. Yeah, there you are. Is this Hunter?
Yeah.
Hey, how's it going?
I just had a question. Are acids more common in nature than bases? Just looking at this chart here, we see a lot of acids, but not a lot of bases.
Yeah, let's just say, I can't say that there's more acids than bases, but what I can say is that there's a lot more yummy acids than there are yummy bases. I don't know if that made any sense, but I think the point of this is to relate this stuff to us. And we know vinegar, you know what I mean? We know orange juice, we know tomato juice, coffee, pea, milk, all these kinds of things. But when we start getting into bases like soap for washing your hands, I think it's a pH of about 9. What do we got there? Windex, a pH of about 10. When you start getting into pHs like oven cleaner, is bad stuff. That's in about the 13 range. The pure sodium hydroxide pellets. Oh yeah, man, you can't get any worse than these. So to answer your question, household stuff, I think there's more stuff that's acid than base, because bases, think cleaners. That's it. Yeah, I guess you're right. I've never looked at it like that. But yeah, good question. Anything else, Hunter?
No, just my curiosity to find, if nature had a preference.
Yeah, I think for the household stuff, there's a lot more acids going on. That's what's going on. So that's the best I can do with that one. Let's have a look here. These are the formulas there, again, that we're going to use. Okay. And these aren't too bad. It's just a matter of plugging and playing again. All right. Calculating pH. Now, I was up there past couple days trying to hopefully make this the calculations. Next week, I'm definitely going to get the whiteboard going because we got some good calculations there. But question is, calculate the pH. Okay. If I give you the hydrogen concentration. All right. So in this case here, the hydrogen ion concentration is 1 times 10 to the negative 5. You could punch the whole thing into your calculator. But if there's a 1 here, this is actually really easy. If it's 1 times 10 to the negative, or 1 times 10 to the negative 8, your pH is just the positive number of whatever the exponent was. You don't even have to do a calculation for that one. Don't need a calculator. But you can. You could input negative log 1 exponent negative 5, and it will give you, try it. I'm going to try it just to make sure. Negative log, okay, and 1 exponent negative 5. If you can't get that, then email me and we'll set up a thing, okay? Try this one out here. Here, if I give you the hydrogen ion concentration is 2 times 10 to the negative 5 molar. That's square brackets, by the way, always means concentration, always means molarity. Square brackets. So you look here, hydrogen ion concentration is 2 times 10 to the negative 5. There's no 1 here, so even I can't figure this out, in my head. So input the whole thing into your expression. Negative log 2 exponent negative 5. This is how you input it into your calculator. Try it out. Take 5 seconds. Negative log 2 exponent negative 5. 4.69. All right. That's how this one goes. And these ones here, you can kind of guess to see what they will be. If you read this pH, it was between the number and the next lowest number, which is 4 and 5. But you guys can have a look at that. Try those out. Just a matter of plugging and playing. Calculate the pH of a 0.015 molar H plus solution. So, easy peasy. There's your hydrogen ion concentration, molarity. Plug it in. Bang. Okay. I'm not really in an in-class test. I'm more worried about things like this, like significant figures and all that. But that's not an objective of my course there for this term, being virtual. So you're just going to choose the right answer, A, B, C, or D. What do we got here? What is the pH of a 0.02 molar hydrochloric acid solution? Okay, so this is a strong acid. So strong acid, easy peasy. Just punch it right into your formula and away you go. There. What is the pH? Now, you have a look here. I've given you the concentration of hydrochloric acid in this solution. But what I want you to know, and this is why I was harping on this about it being what's the difference between strong acid, weak acid, strong base, whatever. Now, you have a look here. This is a strong acid, hydrochloric acid. What's my percentage of breakage? It's going to be 100%. So I have 0.02 molar solution of hydrochloric acid. But because this is 100% breakage, I have 0.02 molar solution of hydrogen. Because I had 0.2 molar, I put it into my solution, it completely breaks, so 0.02 moles of hydrogen. So even though I didn't tell you this, I am telling you this, and this is one of the things I want you to look for. I didn't give you the hydrogen concentration, but because that this is a strong acid, I did give you the hydrogen ion concentration. Okay? That one there you will see again, and I want you guys to realize that a strong acid, 100% break. So in this case here, this is my hydrogen ion concentration. Plug it into here, get your answer. And what is the answer? 0.02 negative log 0.02. 1.69. Okay? So 1.70. All right? Yeah. For your guys' tests, see, I used this there last year. I would be after them about sig figs, but I'm not going to be too hard on you guys about sig figs. So in a situation like this, this would probably be 4.7. So now what's your answer? I got 1.69. So C is the right answer. Let's move on. Okay. What is the pH of a solution of sodium hydroxide that has a hydrogen ion concentration of 2.5 times 10 to the negative 11? How would we do this? What is the pH? So you're going to do this the same thing as you're doing there with physics. I'm looking for pH. Where are my formulas there for pH? Okay, I got pH is equal to that, and I got pH is okay. So I'm going to use these formulas of a sodium hydroxide solution. Now, you think sodium hydroxide solution, is this going to be basic or acidic? It's going to be basic. So where do you think my pH is going to be? High or low? My pH is probably going to be high. Okay? So that's, and part of this, you know, it's a puzzle, right? I'm giving you clues and you got to find, that's all this is, just a puzzle. And you got to predict your own answer. Because if you get an answer, what is the pH concentration of a solution of sodium hydroxide that has a hydronium ion concentration of 2.5 times 10 to the negative 11? Like, you look at that number, 2.5 times 10 to the negative 11. That thing is off the charts small. And that's your hydronium ion concentration. Okay? So this is what we want you to know. And you'd use this formula again. pH is equal to the negative log, and you input your hydrogen ion concentration, which is right here, and you'll get an answer. Anybody get the answer yet? And you look at my answers here, they're all pretty good. Negative log 2.5 exponent negative 11. So I got an answer of 10.6. All right, and in your case there, you would have one answer. All right, I might give a negative 10.6 just to confuse you, but your answer is 10.6. Don't worry about sig figs there for you guys. There will be only one answer. All right, so hopefully those ones aren't too bad. Just be careful on, see, the English tends to be the trouble. Pull the information out and get rid of the language. Going back to this formula here, KW. And the reason why we have this formula there is that water naturally, what we say, auto-ionizes. And see, you have a look here. I have H2O and H2O. It's not even a solution. They're just sitting in a beaker, a glass of water. And what will naturally happen is a hydrogen from here will jump onto here. It just happens naturally. Okay? So we get this already, which why water at a pH of 7 does have hydronium, and it also has base because it auto-ionizes. And whatever the concentration of hydrogen is times the concentration of base, you always get this number. All right? Because this is 1.0 times 10 to the 7 times 1.0 times 10 to the negative 7 will always give you this. So in this case here, this is for a pH of 7, but this formula works for all pHs. All right? And we'll show you some of these right here. We have a look here. This is a really, really good slide to try and understand this. And start over on this side here. Go to a pH of 7. You're kind of working backwards here. So there's your pH of 7, which is also pOH of 7. I'm not going to worry too much about these, but... And you look at my Kw is the same for all different pHs. But if you look at the concentrations of OH and H+, 1 times 10 to the negative 7, 1 times 10 to the negative 7. They're equal amounts at pH 7. But let's go down to a pH of 4. So we're getting more acidic now. My Kw is still the same. Still the same. And have a look at my concentrations though. 1 times 10 to the negative 4 of H+, which still seems like a small number. But look at the amount of OH that's in the same solution for a pH of 4. It's 1 times 10 to the negative 10. And you look at how much smaller this one is. Again, if you multiply them together, you always get this number. So the whole point, this formula here, if you have the concentration of one hydroxide or hydrogen, you can always, always, always figure out the concentration of the other. So let's have a look here. Using these two formulas, calculate the hydrogen ion concentration in a 1.52 molar NaOH solution. Whoa. Now, I've got a basic solution here with a molarity, and this is a strong base, but how am I supposed to figure out the hydrogen ion concentration? Well, this is a strong base. It's going to 100% break up. So whatever number is out here, this is the concentration of OH because it's an OH solution. So you use this formula. H times OH is equal to 10 to the negative 14. Plug it in. You get your hydrogen concentration. Okay? And that's it right there. Try the only way to truly understand these is to get your fingers on the calculator because you've got to get used to how these work. All right? And the formulas aren't bad. You'll see here it's A times B is equal to C. All right? There's only 3 components to this formula and 1 is given always. So I'm going to give you 1. In this case, I gave you that. You solve for this one. Calculate the pH of a 0.152 molar NaOH solution. So here I'm asking for just the pH of this solution. Well, pH is equal to the negative log of the hydrogen. Well, we found the hydrogen here. So you plug that in, and there's the number that it spits out. Now, please be careful. This is like a multi-step question. All right? And go back. Does it make sense? If you see a pH of 12.182, pH of 12, that's going to be pretty basic. Right? Does that make sense? Calculate the hydrogen ion 1.52. Yeah, it does because that is a basic solution. So there's our pH there. Try these out. It's all just a matter of trying them all out. Scientific notation. What is the hydrogen ion concentration in a 0.0 0.00010 molar solution of hydrochloric acid. Well, this is a strong acid. 100% breakage. There's my molarity. That is my hydrogen ion concentration because 100% of it broke. And here I'm just asking you to flip this into scientific notation. So we like our decimal place right here. Number is less than 1, so the exponent will be negative 1, 2, 3, 4. 1.0 times 10 to the negative 4. Okay. What's the OH concentration in this solution? Well, again, strong acid. There's my hydrogen concentration. Plug it in, play. Okay. It's probably to the 10. Okay. There we go. Titration. This is something there that it's actually really fun in the lab because we use acid-base indicators. There's one there called phenolphthalein. Okay, it's clear in an acid and purpley in a base. And it's just the whole thing of being able to, if you have an unknown, how much acid am I going to use to neutralize? That's what a titration reaction is. And we do it with all this specialized equipment. There's a video right here which I can't play, but please watch the video. It's badly dated, it's very old, and it's quite annoying, but it shows you what a titration, what you're actually doing in a titration. And I'm going to explain it to you right here, but I'm just kind of talking in the wind until you see the video. Titration measures the volume of one reagent required to react with another. And it all has to go back to your molar ratio. Remember your molar ratios? That's how these things work. A titration is used to determine the amount of acid or base present in a sample. We use an indicator to tell the equivalence point. If I got 5 molecules of acid, well, in order to neutralize those 5 molecules of acid, according to my chemical reaction, I need 5 molecules of base. And when you see something like this, there's your pH of 7. That's a neutralized reaction. Please have a watch of the movie. I would like to watch the movie with you. I've seen it a million times, but it's good. It details the point of what a titration reaction is. It's the equivalence point, trying to find how many moles of acid are equal to the amount of moles of base, so that we have a pH of 7. All right, and have a look here. What we've got is you will see this. It's on your assignment. You'll see it on the test there, week 7. A titration. Okay, we're looking, and I usually say the word titrate. So if you see the word titrate or titration, ding, 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 you want this formula, which is the same formula there from last week. Dilutions. We use the same formula for titrations. Okay? And so if 22.59 milliliters of 0.1096 molar hydrochloric acid is used to titrate 25 milliliters of an unknown sodium hydroxide solution to a phenolphthalein endpoint, what is the molarity of this? Now you're thinking, oh my God, this is crazy. How can I do all this? Whenever you see the word titrate, ding, you want this formula. Okay, so pull this formula down here. So you got it. M1V1, M2, V2. Now start plugging and playing. All right? So if 22.5 milliliters of this, so 22.59 milliliters, change it to liters. As it turns out, you don't have to, but we'll get into that. So there, I plug that in here. So that's in for volume 1. My molarity of hydrochloric acid is here. So I got this whole side done. They gave me 25 milliliters of NaOH. So that'll go in for volume 2. There's my literage. What am I looking for? What is the molarity of NaOH? And that'll be M2. Flip this guy around, solve away. So the molarity of the NaOH solution is 0.099 moles. Molar solution. Now, I have to say, you can't do these titration questions unless you have a chemical reaction. Because this one works. Look at my molar ratio. What is my molar ratio here? Have a look at it. 1 to 1 to 1 to 1. So it's 1 to 1. So everything's cool in the gang. Whatever number comes out here, that's the answer. Have a look at this one. What is the molarity of sodium hydroxide solution if 21.93 mils of NaOH is required to titrate? Oh, hold on. I'm not even going to finish the question yet. I'm going to get my formula ready to go. Bang. There we go. Now, plug and play. What is the molarity? Okay, so I got my milliliters. Okay, what is the molarity? So there's my milliliters, and I can change to liters. There it is right there. I don't know. It's asking for the molarity, so that one's going to stay unknown. And here I got 26 mils of 0.50 oxalic acid, and they're all in here. Solve away. We solved molarity of the NaOH solution is this crazy number. But before you go and fill in a bubble, you go back and make sure about your molar ratio. Because you look, 1 to 2, so wait a second here. This is only for a ratio of 1 to 1. If I'm looking for how much sodium hydroxide, which we are, I need to double it. So just put there, when you're doing titrations, put a little note. You don't have to memorize it. You've got your pages all around you for your test and all this kind of stuff, right? So here's my titration pages over here. However you want to organize it, just put a note on there that when you're doing titration questions, watch out for the molar ratio. Because if the molar ratio is 1 to 2, you may have to double it. If it's 1 to 1, easy peasy. Okay? And you see here, we've been dealing, I gave you, this is milliliters and molarity. All right? This question right here. Sorry, I want to go back to this question right here. Remember this question? The very first one, 1 to 1. Easy peasy, right? Plug it in, play. Molarity, volume, not a problem. Well, have a look. This is the same question written 4 different ways. Because you guys are now at that point where, yeah, this is probably, we're getting into the meat of the course right here this week and next week. So, where is my, hey, did I delete all those? Chem formulas. Have a look. Now, you remember last week there when I put circles all around? So I had moles here, I had moles here, I had moles here, and moles here. So there's 4 formulas that have moles. So you better be able to flip from one to the other, because this easy peasy question is what we did there on slide 50. But have a look here. Here I have 0.1096 molar hydrochloric acid. I could also write that in moles. Okay? I could also write that in molecules. What would you do if it was in molecules? Change it to moles and then into molarity. Here I've given you grams of this. What would you have to do with this? You got to change it to moles and then into molarity. All right? So just be careful, and all these questions are fair game. They're all the same question as this one, but this one here I've given you an extra step. You have to calculate the molarity. This one here I've given you an extra step. You've got to change molecules into moles. And here I've given you the same amount of steps. You've got to change grams into moles before you can do anything. Okay, so that's where we're at now. We're able to play this game with grams, molecules, moles, molarity. There's molality, but we don't really use that too much. So what is this one? What is the concentration of a nitric acid, strong acid, solution if 10 milliliters of the solution is neutralized by 3.6 milliliter 0.20 NaOH solution? So, we don't have a chemical formula. We don't have a react. I don't know what's going on here. So you need to do it yourself. NaOH plus HNO3 produces acid base will always produce H2O plus, what are we going to produce here? Sodium nitrate. Sorry. Okay. Make sure that everything is balanced. Sodium, sodium. I got 1 water. Okay, everything looks good. What's my molar ratio? 1, 1, 1, 1. Easy peasy question. Let's go. All right. So here I didn't give you this, but you should be able to get it anyway. All right. We're almost done. It's a long one there today. It's a bit of a beast. Neutralization reactions. We've kind of already covered this. You know, acid base produces salt and water. Okay. There's a couple new things here. This is not bad. How do we figure out what is really going on in this reaction? Because you see you got an acid and a base produces, but what's going on? What is the crux of the matter? Well, we need to figure out the net ionic equation. And you'll see here that if I break all of these guys into their ions, so first thing you do, hydrogen and chlorine, break it. Aqueous, aqueous means it's in water. Sodium hydroxide, break it. Aqueous, aqueous means in water. Produces H2O. There is no aqueous. It's just a liquid because that's water. And here I've got sodium and chlorine. Break them. So now you've broken everything up into its ions that you possibly can. You got this guy here. Now I call it the slice and dice. Slice and dice whatever is the same on each side. So I got a hydrogen here. I got no hydrogen here. Leave it. I got a chlorine here. It's gone. Gone. Slice it. I got a sodium ion here. I got a sodium ion here. Dice it. Get it out of here. And so all you're left with at the end of it all is this. So ultimately, this whole bag of marbles right here, the only thing that's going on is this. And that's what we call your net ionic equation. You see these other guys up here? They're not doing anything. We call those spectator ions. Get them out of there. We don't do anything with them. They don't do anything for the reaction. This is the reaction. And let's have a look here. These ones here, you just try them. Don't do a million of these. Try a couple of these and they become really cake. So here is this guy. Okay? Your total ionic equation. Break it. And you see here barium chloride. Barium 2+. And see I got 2 chlorines. Why? Because there's 2. All right? And then I got sodium sulfate. 2 sodiums and a sulfate. And you'll see here barium sulfate. It's a solid. No touchy. Leave it alone. It's a solid. If something's a solid, you can't break it into ions. And then you break the sodium and then slice and dice. So ultimately, the reaction is this. Everything else is a spectator ion. Same thing here. Y'all can try these out, okay? See how they all go. Here's another one. What is the net ionic equation for hydrobromic acid reacting with potassium hydroxide? So here, I didn't even give you the compounds chemistry. So you got to make their chemistry. You got to make the chemical reaction. You got to find the products. Then you'll have to break them into ions, slice and dice, and find out your net ionic equation. Try that one. Let me know if you can't get it. And I apologize, it was quite long, but next week won't be a slice of pie either. But after that, it should be pretty good. Let me know how you guys are doing. Please be vocal. Please let me know if you guys are having difficulties. And other than that, we are good to go. I will post this onto YouTube immediately. And if you guys got nothing, I got nothing. And your assignment's open.
I have a question. What's the best way to get a hold of you? Do you have an email on WebEx somewhere?
No, just email me. My here, if you guys don't have it, I'll write it right here. There you go.
Perfect. And on the assignment, I was just peeking at it. I think I missed at the beginning of the class, but that bubble chart, is that the only page we send back to you once we're done?
Yeah, that's, I'm not going to put that out to the weekend. And so it just gives you guys time there to toot around. And so just hold on. Do the assignments there for a couple days. And I'll shoot a, it's not due for 2 weeks. So take your time, nail it, talk to each other. And I'll send the bubble sheet out there, I don't know, whenever. And I'll let you guys know. And you guys can upload it through that. But other than that, just take it easy. And yeah, this stuff here today, everything next week will be a carry-on from today. And you can see how we just jumped it up a little bit. Next week, we'll jump it up a little bit more. But I think you guys can, I know you guys can do this. Just practice these a little bit. And the key is strong acid, weak acid, being able to know the difference. And other than that, I think you guys will be fine. Let me know. Talk to me. Questions? Love it. Love it. If you guys got anything, let me know. I'm going to sign off because I don't even know if my kids have eaten lunch yet. I'm sure they have, but they're quiet, so yeah, I think I should go check on them. But anyway, you guys are great. I'm going to stop recording. I'll post this now, and keep me posted on your progress. Don't be shy. Take it easy, guys.